Okay, so hello everybody. Welcome to this talk at the Chemnitz Mathematische Kolloquium. It's a great pleasure to introduce László Székelyhidi to you. He's from the University of Leipzig, just around the corner. A little info on his career. So he studied mathematics at Oxford, where he received the Gibbs Prize. His PhD he earned at the Max Planck Institute in Leipzig under the supervision of Stefan Müller. As a postdoc, he was in Princeton at the Max Planck Institute and at the ETH Zurich, where he also became docent. From 2007 to 2011, he was professor at University Bonn. And since 2011, he is our neighbor in Leipzig. From the numerous awards and honors, I mentioned just a few. So he is a member of the Leopoldina. He received an Oberwolf Prize in 2011 jointly with Nicolas Gilly. He was an invited speaker at the ICM in Seoul in 2014. Got an ERC starting grant as well as an ERC consolidator grant, and the Leibniz Prize in 2018. It's a great pleasure to have him today, and I open the mic for László. So thank you for being our speaker today.
Thank you for this very nice and generous introduction. And also thank you for the opportunity to present my work in this talk. Let's hope that sometime in the future I will be able to visit Chemnitz in person. So the title of my talk is Convex Integration for Fluid Dynamics. Convex integration is a technique that originally arose from the work of Nash on isometric embeddings, and then generalized by Gromov to various problems in geometry and topology. And let's say around the last 10 years, it was introduced to PDE in fluid dynamics, and has served to provide tons of counterexamples to certain questions. Counterexamples in the sense that this typical statement is that there is a non-unique, in fact, infinitely many weak solutions of a certain class to some PDE. As a result, because of these counterexamples, it has also somehow fallen in disrepute. A little bit as, you know, it's a devil's tool to just produce counterexamples, and has nothing to do with the real fluid dynamics. And so in my talk, I want to convince you of the opposite, that there are certain ideas behind this technique which actually are very much relevant for fluid dynamics. At the same time, let me also say that I will not really explain what is convex integration. So think of it as a kind of pretty much black box for producing lots of solutions to a certain nonlinear PDE under certain conditions. And I will concentrate on these conditions. Okay, so to start with, I want to give you some examples of typical questions in fluid dynamics, very classical questions. And my motivation here is this very nice quotation from Thomas Brooke Benjamin, who was a famous fluid dynamicist in Oxford, who wrote in 1978, "In this subject, there are distinct and sometimes ill-matched styles of scientific inquiry, and their more effective alliance is still an outstanding objective." So what he was talking about is that we have certain very nice theorems about models in fluid dynamics, and we have a lot of observations, but the theorems do not really match the observations. And I want to give some examples of this. So the most classical question related to fluid dynamics is to calculate the drag force for the flow around the sphere. So this already appeared in the work of Newton. And so to formulate the problem exactly, imagine a ball of radius L in a uniform flow of air or water or something, which is approaching at speed u. Or you can think of the air being stationary and the ball just flying with speed u. And the question is, what is the force exerted, I mean, the resistance force exerted on the ball by air, or the other way around? So Newton provided a formula in his Principia in the 17th century, and his formula is that F is proportional to rho, the radius of the fluid, times L squared times U squared. So almost 100 years later, D'Alembert also looked at this problem, and he gave the answer F equals 0. There is no force, at least in the case of ideal fluids. Ideal fluid is a fluid where there is no internal shear forces. So there's no viscosity on the fluid itself, of the fluid. And Stokes, yet again 100 years later, also looked at this problem and provided this third formula, which involves rho again, the density, the viscosity nu, and times L times U. And in fact, you can check that Stokes' formula agrees with D'Alembert if you put nu equals 0, but they look very different from Newton's formula. Now, it turns out that the derivation of these three formulas are somewhat different, but D'Alembert and Stokes used the PD, the underlying PD. So this is the underlying set of equations is the stationary Navier-Stokes equations. So U is the velocity, the local velocity, the little u, and pressure P, and there's a viscosity nu. And in fact, D'Alembert's and Stokes' derivation use this equation. Newton's derivation, however, does not use the equation. It was, I mean, derived before the equation was known in this form, and it's based on dimensional analysis. Now, who was correct? It turns out that everybody was correct. So in order to understand this, we have to introduce the Reynolds number. This is a dimensionless number which represents somehow the nature, I mean, the level of turbulence of the fluid. How turbulent is the fluid? And so typical examples are a golf ball flying through the air would be like 10 to the 5, 10 to the 6, so that's pretty large. A car driving at normal speed, like 50 kilometers per hour, would be 10 to the 6, 10 to the 7. Now, the difference between high Reynolds number and small Reynolds number is roughly explained here. At small Reynolds number, the flow is consisting of nice smooth streamlines. It's called laminar. So this would be a typical low Reynolds number flow across past the sphere. And this is the lower picture is what you expect at high Reynolds number. But you see high Reynolds number 10 to the 6 is sort of everyday situations. And in this case, behind the sphere, there is a turbulent wake forming. That's something that happens in everyday situations. And it turns out that in the low Reynolds numbers case, Stokes was almost correct. His formula is pretty much the correct formula. I mean, correct in the sense of agrees with experiments. And in the high Reynolds number case, Newton was almost correct. Okay. A second example is something you can try at home with your children. Take a ping pong ball, table tennis ball, and a straw, and by blowing on the straw up and put the table tennis ball above the straw, you can balance it by just blowing and balancing it in the air. And what's interesting about this experiment is that it's not so difficult to do. And that is an indication of the fact that this vertical position, when the table tennis ball lies directly above the straw, is a stable position for the ball. So small deviations are easily corrected. The ball will go back to the vertical position. So this is a nice picture of something slightly different setting of the same experiment by my colleague Jonas Hirsch, who's also professor in Leipzig for analysis. So it turns out that this experiment does actually appear in some physics textbooks, high school textbooks, with the wrong explanation. The explanation given in textbooks is often that, well, it's to do with the Bernoulli law, the constancy of the pressure along streamlines, but so that would mean that you have sort of a lower pressure here than here, and so you have a kind of pressure drop which is causing this stability. But that's completely wrong. The easiest way to see that that's completely wrong is that you can actually calculate the solution of the underlying partial differential equations. This was done by Landau, the famous Landau of the Landau-Lifshitz books, and so here the PDE is again the stationary Navier-Stokes system with a right-hand side, which represents the external force of blowing, blowing out of the straw. And of course, what he considered is the idealized case where the radius of the straw goes to 0, but still there is a fixed amount of force coming out of it. So there is a Dirac delta here. Now, you can calculate, so he could calculate the exact solution to this system. And out of that solution, you can work out what is the pressure distribution on this lateral plane. And it turns out the pressure has a maximum on the axis of symmetry, which should imply that this is an unstable position. So this is not what happens in reality. Okay. So again, there's a mismatch between what we observe and what we can prove. Okay, the third example is concerning the law of finite energy dissipation in a turbulent flow. So here I have written the full Navier-Stokes, the full Navier-Stokes system. Let's assume periodic boundary conditions in 3D. Now, a classical computation, which you get by multiplying this first equation by V itself and integrating, is that the energy dissipation rate of a smooth solution of the Navier-Stokes equation is given by nu, the viscosity coefficient, times the integral of the gradient V squared. Okay, so in order to test this experimentally, one has to again use the Reynolds number in order to non-dimensionalize things and get, when you measure something, get a non-dimensional quantity out of that. If one does this, then the experiment tells us that as the Reynolds number goes to infinity, which corresponds, as you can see, to the fact that nu goes to 0. If nu goes to 0, the energy dissipation rate should go to 0 by this formula. But it turns out that it does not go to 0, it goes to some finite, non-zero number. That's what the experiments indicate. Of course, you can never go pass all the way to the limit, but experiments seem to indicate that this quantity does not go to 0. By the way, this fact that it does not go to 0, if you assume that there is a non-dimensional quantity here, then that will agree with Newton's drag formula, the formula that Newton derived for the force on a ball flying in a stationary flow. Okay, so here there is again a problem between what we see from the equations and what we observe in experiments. So this is the type of thing that Brooke Benjamin was talking about. Now, somehow the problem with the theory that I presented is that it applies to smooth solutions. If you take a smooth solution, you can make these calculations and end up with the wrong answer. I mean, wrong in the sense of experiment. So one has to look at weak solutions. And here I want to cite John von Neumann, who very aptly formulated the point about weak solutions or turbulent solutions. One has to talk not of one turbulent solution, but of many turbulent solutions. There is probably no such thing as a most favored or most relevant turbulent solution. So what he's hinting at is that, of course, in PDE, we are very much focused on the question of uniqueness once we prove the existence of a weak solution. But when turbulence is involved, what Neumann is telling us that the question of uniqueness is maybe overrated. One should ask different questions. Let me also mention that the notion of weak solutions is actually a very old notion. So already Euler was looking at weak solutions, although they were not called as such. But Euler did understand that singularities may appear where you're not able to differentiate the equation. So you cannot make sense of all the derivatives appearing in the equation. In fact, when he derived in 1757 the Euler equations, so this is the equations of motion for an ideal flow, it is just based on the conservation of mass and the conservation of momentum. And his derivation in modern language amounts to the continuum formulation, which passes via test regions. So the conservation of mass amounts to the statement that this red one, that through any fixed subdomain of the full domain where the fluid is living, the amount of stuff going out is the same as the amount of stuff coming in. So it's an integral over the boundary of the normal component of the velocity, and this should be 0. That's conservation of mass. And then, of course, if you use the Gauss theorem, you get the integral version. Divergence of u is equal to 0. The same thing with the momentum. The total amount of momentum passing out of a region has to equal the total amount of momentum coming in. That's the second red integral. So if we pass to the PDE formulation, we need to be able to talk about derivatives, but we could also just stick to these red equations as the definition of a solution, and then all we need to be able to do is talk about the value of the velocity and the pressure on boundary of domains. So no differentiability is required. The notion of weak solution is, so this is a slightly historical footnote. The notion of weak solution is even older than what I've just mentioned. D'Alembert, I mean, probably the first PDE that was ever written down is the one-dimensional wave equation, the equation for a plucked string. And D'Alembert derived the general solution of this equation. It's given by the sum of two traveling waves, one wave traveling to the right with speed c and the other one traveling to the left with speed c. So in particular, he proved that for arbitrary functions f and g, this formula gives a solution of the 1D wave equation. On the other hand, he said, well, since I have two derivatives here in the equation, f and g have to be twice differentiable. And there was a very famous, I mean, now famous historical fight between D'Alembert and Euler. Euler was saying that you should allow for situations where f and g are not differentiable. In particular, they were considering the case of a plucked string. If you pluck it just in a single point, then the initial data is a triangle. So it's not differentiable at the place where you pluck it, and then you let it go. And that should also be a a situation that is reflected by these solutions. Now, later on, Lagrange gave another proof that even for non-differentiable f and g, these are valid solutions. His proof would be something that we might now call notion of weak solution by test functions. You multiply with the test function and we integrate by parts. Analogously to what I just showed for the Euler equations. And Jean Larrey in 1934, in this very famous paper, defined that notion also for the Navier-Stokes equations and proved the existence of weak solutions. There is another weak formulation which is based on Fourier expansion, Fourier series. This was done by Fourier himself for the heat equation, and Onsager in his work on this law of energy dissipation that I mentioned earlier also came up with a definition of weak solution based on just Fourier series. Okay, so this is a small historical footnote. Now coming back to what happens with weak solutions in fluid dynamics, if you're not careful, you will obtain nonsense. So here is the first example. It was a paper by Scheffer in the 1990s, which we looked at later with Camillo Dell'Ellis, that there exist non-trivial weak solutions of the Euler equations with compact support in space-time. So they are weak solutions, they are non-trivial, so not the identical zero solution, but they have compact support in time. This is the important. Compact support in time means that the solution is zero, then it's not zero, and then it's zero again. So it clearly defies all physical intuition. It cannot be the case. Even just considering the case that the energy should be conserved for smooth solutions of the Euler equations, but it should certainly not jump up. Even if for weak solutions we could assume decay, it should certainly not increase. So this is a non-physical, let's say, nonsense solution. It gets actually worse. By the same technique, one can prove that given any two velocities, v0 and v1, velocity fields, there are infinitely many weak solutions of the Euler equations that start at time equals 0 at v0 and end at v1. So, from any velocity field, the dynamics can reach any other velocity field. So there's basically no evolution. There's nothing, the equation doesn't tell us anything in a sense. So this type of solution is clearly unphysical and should be ruled out somehow. So I should mention that the technique to obtain these results is convex integration, but Scheffer didn't know about the terminology of convex integration, but his proof is sort of already, it was ahead of his time, but it's already anticipating this technique. The same thing was recently proved for the Navier-Stokes equations. So with Euler, you might say, well, it doesn't belong to the nice category of equations because it doesn't have a dissipative term. Navier-Stokes is, in first approximation, if you don't pay attention, more like a parabolic equation, so we could expect more nice behavior. And they were able to prove, Bookmaster and Vicol in last year, it was published last year, that the same thing happens for the Navier-Stokes equation. So there exist non-trivial weak solutions with compact support in time. And also, you can get from any initial velocity to any final velocity. Also with weak solutions of the Navier-Stokes equations. Now, one has to be very careful with what is the definition of weak solution. So far, I told you that it's just a way to, let's say by test functions or discussing distributional derivatives, if you can make sense of the equations in a continuum way, that's what weak solution means. Now, so it's not the weak solution that most people, and in particular the Millennium Prize on the Navier-Stokes equation is concerned with. I'm coming to that. So now I gave you several examples now of very bad unphysical solutions if you're just in the realm of weak solutions. So you might be inclined to think one should stick to classical solutions. They are not going to be as wild as this. But then I also give you an argument that classical solutions are not able to explain all the phenomena that we observe. So what I want to, my main message in this talk is that instead of concentrating on the actual construction of these weak solutions, one should try to understand what type of weak solutions can make sense physically. And my point is that this is related to weak stability or closure of the equation. And because what I'm saying is somehow motivated by the work of Luc Tartare, I want to cite this nice sentence from him. The only thing about turbulence that everybody agrees upon is that it is created by oscillations in the velocity field. Now, Tartare's work, originating in the 70s and 80s, concerned understanding oscillations and how it affects nonlinearities in the equation. And that's a very important point in this subject, at least in my mind. So in the turbulence business, oscillations are somehow treated as random fluctuations. So if you open a typical book on turbulence, you see the Reynolds decomposition. Let's say V is a velocity field of a turbulent flow. Then one imagines splitting that into a kind of average. The average doesn't have to be fully defined. It could be an average over a long time or over certain regions of space or over ensembles, so averaging over different experiments, and then a fluctuation. And a lot of works are concerned with fluctuation being random and the average being something deterministic. Now, if you make this decomposition, even without specifying what is the average, you end up with something like the Euler Reynolds system. Or of course, you could also end up with the Navier-Stokes Reynolds system if you add here nu times Laplacian of V bar. Okay, but the Euler Reynolds would be without the Laplacian term. And the key point is that since you obtain it by averaging the equation, if you average this quadratic term, it's not the same as first averaging and then taking the product. And the difference is this, what is called the Reynolds stress tensor. It appears as an extra defect in the equation. This is divergence of R. So, if you can check easily that I've not really done anything here. But roughly speaking, this R encodes the amount of information that the fluctuation provides back onto the average. Okay, so this is the average stress of the fluctuation. If there was no fluctuation, then we would just have the average, and this would be 0. Okay, and the key somehow issue in the turbulence modeling business is to find an equation for this R bar, because you see now I have an equation with too many unknowns. I have this R. And the only thing we know about R, just from this averaging, is that it's a non-negative symmetric tensor. So now a kind of black box result on convex integration is that if we assume not only that it's not 0, so positive semi-definite, but even that it's positive, strictly positive, a positive symmetric tensor, 2 tensor, then that's what lets us call this a strict subsolution. And out of this strict subsolution, we can obtain back weak solutions by somehow reconstructing the fluctuations. And this is more or less a black box of which I call convex integration. And a typical statement is that any strict subsolution of the Euler equation can be weakly approximated by continuous weak solutions of class C 1/3 minus something, so it's up to, you have to choose some exponent slightly less than 1/3, and this type of statement was important because of Onsager's conjecture. So this is related to Onsager's conjecture, which is related to this law of decay of energy, but I don't want to go too much into that business in this talk. Okay, but somehow you can think of this statement also as saying, if I take the closure of weak solutions of this class, I will obtain all these subsolutions. I will get into this bigger class, which are not necessarily solutions anymore, but there is some R which has to be positive or semi-positive. Okay, so in the remaining of my talk, I want to give some more recent examples of this idea of looking at an equation and a certain class of solutions, and then taking somehow the weak closure of this class of solutions and seeing what we get. And in some cases, you see that you will end up with something that does agree with experiments. In other cases, you have to be more careful. But the key issue is what I will call the compactness, and this is related to Tartar's old work. So the first example is the three-dimensional Navier-Stokes equations. Okay, in this slide, I just want to recall what Leray did in his paper in 1934. So he defined global weak solutions, so they exist for all time, which he called turbulent solutions. So he clearly had this idea of turbulence in mind. So here are the Navier-Stokes equations. There is an initial data given, some V0, and his proof, so Leray's proof of the existence of a weak solution, proceeds by 3 steps. The first step is to derive some kind of a priori bound on the possible set of solutions. So if you take, I mean, this is related to the energy dissipation calculation that I showed some slides back. So at least smooth solutions of the Navier-Stokes equations will satisfy the energy equality. So in fact, there you will have equality here. And then you could say, well, so I can at least restrict to the class of solutions, weak solutions, which satisfy the inequality. And this inequality gives you an a priori bound on all possible solutions, because this V0 is given. So the L2 norm of the V0 bounds the L2 norm of the solution V at time t, and the cumulative dissipation from 0 to time t. So you could say that there is an a priori bound in L infinity in time, L2 in space, so uniform in time in L2, and in L2 in time and space of the derivative. This is L2 of H1. Okay, that's a very important first step. Then in the second step, one has to come up with some kind of approximation of a solution. I mean, we want to construct a solution, so there are there are 2 classical ways. Either this is by a finite dimensional projection, Galerkin approximations, or by regularizing the equation itself, as Leray did in his paper. So this epsilon means that there is a mollifying kernel. So V epsilon is modification of V. Okay, and the important point in both type of approximations is that the energy inequality should still be valid. So now we left the realm of solutions. We have a bigger set of functions, but they should satisfy still the energy inequality. And because of this, one can then pass to the weak limit. So as the approximation gets finer and finer, we have a weak convergence to some limit function, and that function is hopefully a solution. And the only problem is that there is this nonlinearity. But because the embedding of H1 into L2 is compact, this is actually a substantial part of Leray's paper, because 1934 was before Sobolev already. So this is, or he didn't know really. So he proved this fact that the embedding of H1 to L2 is compact. So that allows us to pass to the limit in this quadratic expression and prove the existence of a weak solution with this energy inequality. So now contrast that to the work of Bookmaster and Vicol. Here, so there's non-uniqueness and somehow wild behavior, like this one that you start with V0 and end up with any V1, of distributional weak solutions. So these are weak solutions where the only requirement is that this distributional derivatives should make sense. So V should be quadratic square integrable. And actually their proof gives, it doesn't give the energy inequality as the race paper. In fact, it only produces solutions where you can control the uniformly in time of the L2 norm and uniformly in time the W11 norm. And the point is that W11 does not embed into L2. So there's this compactness step fails. And as such, if I take the closure of the set of such solutions with a priori bounds in these spaces, I'm not guaranteed that I will end up with just solutions. I will end up with a much larger set of functions. And then convex integration somehow allows me to come back from that much larger set of functions and end up with somehow physically nonsense weak solutions. Okay, so that's a big difference between these two. In Laray's paper, I mean, if I take the weak closure of the set of solutions satisfying the energy inequality, I will still end up with solutions because of this compact embedding. That's a key difference. Let me also mention that there's a very recent paper by Cheskidov and Luo on Archive, which constructs solutions in a different class. Now it's, so W11 does not embed in L2, so what about that they can go up to W1Q for any Q finite. So it certainly embeds, this W1Q certainly embeds compactly into L2. However, in time it's only L1. So again, this this Banach space of Tx dependent functions does not embed into L2 of L2. So there is no control of this term. Okay. So the issue is compactness versus loss of compactness. This issue can be explored a bit further if we replace the viscous term in the Navier-Stokes equations by the P Laplacian. So this type of model appears in non-Newtonian fluids. In this case, the energy inequality gets power P in the dissipative term. And so the a priori bound of as in Laray's case, gives us LP of W1P. And this embeds compactly into L2 if and only if P is bigger than 6/5 in 3 dimensions. And indeed, one side of the story was proved by Diening, Ruzicka, and Wolf in 2010, the existence of Larray-Hopf weak solutions via Galerkin approximation and compactness, as Larray did it, if P is bigger than 6/5. And with Jan Burczak and Stefano Modena, we showed that you have the same type of wild behavior, non-uniqueness of Larray-Hopf weak solutions, so now with the energy inequality, but only if P is less than 6/5. So it's exactly this sharp divide between having compactness that gives us existence by this standard approximation techniques, or non-compactness, and then all hell breaks loose in some sense. Okay, my second example is the 2D vortex sheet problem. Now, if you recall the picture from one of my first slides on the drag force on the sphere, there was this turbulent wake behind it, and this is of course very important for many reasons to understand the evolution of this turbulent wake. And one model that people have been using is you take a plane perpendicular to to the incoming flow. This is called the Trefts plane. And the divide, you see that there is a sort of sharp division between the turbulent region and the laminar region. And this divide defines a curve on this plane. And so motivated by this situation, a model problem is to assume that the vorticity is concentrated on a curve in the plane. That would be this curve. So being concentrated means that the vorticity is a measure with some density gamma, which absolutely continuous with respect to the one-dimensional Hausdorff measure. Now, if I know that the curl of a vector field is given by something, and the divergence is 0, I can calculate that vector field by the Biot-Savart law. So this is solving the equation, I mean, sort of anti-curl. It gives us this formula where here I've denoted by star the complex conjugate, because the bar is used for averaging. So this is a complex integral, line integral on this curve. And so that's the starting point of the vortex sheet problem. We assume that the initial vorticity is given by something like this, and the initial velocity is given by something like this. So in 1991, Jean-Marc Delors proved, this was again a landmark paper, global existence of weak solutions if the initial vorticity density is positive. So this gamma is positive. More generally, he proved that if you have omega zeros, the initial vorticity, a positive measure, and you have finite energy, then there's a global weak solution. And his method is again like Lerais' technique, at least in its broad outline. The first point is to get an a priori estimate. Now, in the two-dimensional situation, for the Euler equations, vorticity is just transported. It's a scalar, and it's transported by the velocity. So that means all level sets have the same size for all time, and in particular LP norms, and also the L1 norm and the total mass as a measure remains constant. So that's an a priori bound, that the total measure remains bounded by the initial measure. And then this allows you to pass to the weak limit. Now here, passing to the weak limit is much more subtle than in the case of Lerais, because this space of measures of the vorticity, or let's say even W11, does not embed compactly into L2, which is what we would need again for this quadratic term. However, what Delors observed, and this was then very nicely clarified also by Evans and Müller, is that actually we don't need to pass to the weak limit in all possible products of the components of V with itself, just these special ones. And they turn out to be weakly continuous because there is a kind of diff curl structure. This is an example of compensated compactness. So these terms pass to the weak limit because of this a priori bound, and that's the key point in Delors' proof. Okay. Now this is very nice, but the solution of Delors doesn't really tell us anything about any qualities of this solution. It exists, uniqueness is an open problem, and we don't really know what happens with that solution. So there is another much more classical approach to the vortex sheet problem, which is based on the assumption that the vorticity remains concentrated on a curve. So this is an assumption. This is that does not follow from the equation, and it's not necessarily true in Delors' case. At least we don't know. But if we assume that for any time t there is a curve z and the density gamma, so that the vorticity is given by this curve, and the velocity is then the Biot-Savart of that vorticity, then one ends up with an evolution equation for this curve. This is the Birkhoff-Rott equation. Very nice. It's a non-local, but somehow complex integral involved. But it's a one-dimensional evolution equation, and it turns out to be locally well closed for analytic data. So that's this result is more or less a Cauchy-Kovalevskaya type result. If the initial curve and the initial density on the curve are analytic, then for short time you have an analytic continuation of that initial data. Unfortunately, it turns out to be ill-posed for non-analytic data. So if you take any non-analytic data, then it's quite likely that there is no short-time existence in any space. And this is closely related to the Kelvin-Helmholtz instability. So, which is illustrated here. If you take an exact flat curve as the initial data, then it will remain flat. That's a stationary solution. But if you make, I don't know if you can see, slight perturbations, like a sine wave, then these waves get somehow pushed over each other and amplified, and you end up with this this roll up, and eventually it breaks down. So this is another approach to talk about weak solutions, but it gives us geometric information on how this vortex sheet evolves, but unfortunately it's ill-posed. So in recent work with a Spanish student, Fran Manuel from Madrid, we tried to look at this situation and combine the two techniques somehow. So we can prove the existence and non-uniqueness. It's part of the deal that you get non-uniqueness of weak solutions which satisfy the energy inequality, and the initial data doesn't have to be analytic, and it also doesn't have to have a fixed sign. So our solutions are, so here is the initial data. There's some curve z with density of the vorticity gamma, and for positive time, out of one curve you get two curves which bound an annuli region. Inside that region, the solution is turbulent. It's just a square integrable vector field, in fact bounded but not differentiable vector field. Outside, so in this region, the vorticity is concentrated. The mid curve of this region has an evolution equation, and the region itself is growing at a certain rate, linear rate in time, which we call the turbulent zone. So, I mean, our construction goes via this Euler Reynolds system. So here we have the average velocity field, and there is some Reynolds stress. And we think of this R not as something that has to satisfy an extra equation, as in the closure problem of classical turbulence, but we can think of it as a kind of control parameter. And we assume in our work that the vorticity of the V bar will be concentrated on these two boundary curves, and that allows us to reduce this equation of some solutions to a boundary value problem for this Reynolds tensor. So it should be divergence free in the turbulent zone, and it has to satisfy some boundary conditions. Now, I would just want to emphasize that the right-hand side, this boundary condition, is given by something like this. And this would be zero precisely so this being zero is precisely the Birkhoff-Roth equation. So in some sense, we allow for a flexibility by not requiring exactly the Birkhoff-Roth equation, which leads to the instability, but somehow shift the problem into this R, and then R gives some kind of turbulent vector field inside this region. And so what we obtain is something like this. Let me go back to the beginning. So what you can see is the central light blue curve is a regularization of the Birkhoff-Roth equation, Vortex Blob regularization. So you see this kind of roll up, and the dark blue curves are the boundaries of this turbulent region that we obtain. the red dots are just there to show that there the initial vorticity density is 0. So the vorticity density in this numerics is not constant. It's a maximum to the left and the right, and it's 0 on the North Pole and the South Pole. Just to get something that has a kind of not too much symmetry. And so in some sense, these solutions, you can interpret them as saying that, well, I mean, somehow where this kind of roll-up occurs is not a priori fixed. It's to do with how I perturb or how I produce my approximation. It could appear anywhere. So the wrong question is where it is. The correct question is, how fast does it grow, for instance? How is the vorticity in some smeared out manner diffused beyond the central interface? And these blue lines are supposed to indicate that that's somehow the region where vorticity could end up diffusing to. So it's a kind of bound to possible degenerations of weak solutions. Let me see if I have another picture. How do I? Oops. Here is another movie that shows a kind of zoomed in version of this. So you see how this roll up produces secondary and ternary roll ups. It's a very unstable situation. Of course, the light blue curve can only be obtained by regularization. So it's not the true solution of the Birkhoff rod. But these dark blue curves are true solutions. So they give true solutions of the Euler equations. Okay, so going back to my slides. Yes, so another interesting question here is, again, not uniqueness, but the question of dissipation rate. And we obtain, at least for a short time, a certain dissipation rate. We didn't check with the experiment whether this is realistic or not, but there's a certain dissipation rate that's related to C, which is how fast these curves can separate from each other. Okay, I'm hopelessly running out of time. I have one third example, but this will be quick. So this is concerning magnetohydrodynamics, again in 3D. And so this is you have the Euler equations again for V, dTV plus divergence of V tensor V plus gradient of the pressure equals 0. Here you have divergence of V equals 0, but there is also another field, a magnetic field B, which is supposed to be divergence free. It affects the momentum equation, and it has its own evolution equation. So this is derived from the Maxwell system. Now, this system is somehow, I mean, even though it's more complicated than Euler, because you have this B, it is also more rich in its structure. So there are three conserved quantities: the total energy, which is the integral of V squared plus B squared. This would be the total energy integral of V squared in Euler. You have a cross helicity term, which is the scalar product of V and B, and a third one, which is magnetic helicity, which is a different scalar product, B with its anti-curve. So this A is obtained by the Biot-Savart applied to B. Now, the conservation of magnetic helicity was the subject of Tartare's work in 1977, and more recently, the total energy and cross helicity conservation was looked at by Kaflish, Clapper, and Steele. Onsager type criteria. So I didn't really talk about this, but there are criteria that tell you that if you have a weak solution with some weak regularity, like Euler regularity, then they conserve this quantity and this quantity. But Tartare already noticed that under much weaker conditions, magnetic helicity is conserved. So magnetic helicity is somehow special in this system, and that's also relevant for physics. Now, in physics, of course, you should have some dissipation, some viscosity in the momentum equation, and some resistivity or viscous term in the equation for the magnetic field. And one important cornerstone in the theory is the Taylor-Voltaire relaxation theory. So in typical situations, the viscosity is, I mean, viscosity and resistivity are small, but the resistivity is much smaller. plasmas. And as a result, there are two different mechanisms that appear in the evolution on different time scales. On a short time scale, because the viscosity is quite large compared to the other terms, the kinetic energy dissipates and the fluid goes to rest. The plasma goes to rest. V goes to zero, well, almost zero. And at a much larger time scale, the magnetic field relaxes. So once you have V is equal to zero, of course, not much remains, but you shouldn't really put it equal to zero. The point is that at a much larger time scale, B relaxes to the global minimum of the L2 norm of B, subject to the constraint that the helicity is preserved. And this led to a very rich theory of the topology of such magnetic lines by Arnold and Moffat. Now, what Tartar did in 1977 is applied a version of the Diffie-Kerr lemma to systems like this. You see in the MHD system, this electric field E is B cross V, this equation. And the divergence of B is equal to zero. And the time evolution of this scalar product of A with B gives you scalar product of E with B. And if in MHD E is perpendicular to B, this is zero. That's the magnetic helicity conservation. And Tartar was able to show that this actually holds under weak conditions because there is a difficult structure. And this was then generalized by Faraco and Lindberg in last year, so that even in the inviscid irresistive limit, when these two parameters go to zero, magnetic helicity remains a conserved quantity. Whereas what experiments do indicate is that energy can still dissipate, just like in the hydrodynamic situation. So there's anomalous dissipation of energy and cross helicity, but the magnetic helicity is conserved, which gives you a topological constraint on the possibilities of the magnetic field. Now, with the work, with the techniques of Bookmaster Recoil, together with a PhD student, they were able to show existence and non-uniqueness of weak solutions to the ideal MHD system, which do not conserve anything. They do not conserve energy, they do not conserve cross helicity, and also magnetic helicity. So they are kind of, one could say, I mean, unphysical because of what I just said in the previous slide. In fact, their solutions are in the same space that the Navier-Stokes solutions are. So it's L infinity of L2 and continuous in time with some very small Sobolev exponent, H epsilon. And they wrote in their paper, in the archive version, that there is, however, a fundamental physical reason why the construction in L infinity weak solutions fails. I mean, in the sense of convex integration constructions. And the fundamental physical reason is indeed what I just mentioned, that magnetic helicity should be conserved under the assumption that weak solutions are in L infinity. And indeed, what Faraco-Lindberg showed is that you don't even need L infinity. L3 is sufficient for the conservation of magnetic helicity. Whereas you see here, you only have L2 in the previous slide. Here's L2, and here is L3, and magnetic helicity is conserved. So what we were able to show is that you can still apply convex integration and prove the existence of bounded, so L infinity weak solutions to ideal MHD, which do not conserve energy, cross helicity, but the magnetic helicity is conserved. So they lie in this somehow, of course, they are weak solutions, they are idealized in some sense, but they are idealized in a way that is consistent with the physics. And the key point in the construction is to look at the relaxation. So under the assumption that the vector fields are in L infinity, there is relaxation in the Euler, in the momentum equation, the same as in the Euler equations. You have a Reynolds stress tensor, but you cannot completely relax the magnetic part of the equation. So there has to be this constraint. Remember, in the original equations, E is vector product of the velocity with b. So it has to be perpendicular to b itself, and this is still true in the relaxation. So this is kind of like the analog of the Reynolds system for ideal MHD, and that allows us to produce such weak solutions. Okay, so I hope that I've run out a little bit of time. So, but I hope I was able to convey this philosophical point that it's a question of compactness, and you can study a certain class of solutions, but you should look at the closure of that class under the natural conditions which they verify. So yes, so with this, I thank you for your attention.
Okay, thank you, László, for this fascinating talk. I welcome questions, remarks, both by just speaking up and using the chat function. Okay, then let me ask at least first of all one question. You talked about this Reynolds decomposition and the different ways of averaging. So you said there are different ways of doing an average. Is there some kind of ergodic principle behind that you can say that it doesn't matter so much which way of average you use?
Well, this is, nothing is proved as far as I know. But this is certainly an underlying assumption in a lot of the physics literature. In fact, when people measure the distribution of the velocity in a turbulent fluid, they don't measure the velocity at different points. They measure the velocity in one point for a certain interval of time. And that gives you a kind of statistics of the distribution of the velocity at that point. But then there is an underlying assumption, which is called the Taylor hypothesis. It's a different Taylor, it's G.I. Taylor, that this distribution should be the same as if you would take the velocity at different points at the same instant of time and then look at that distribution. So this is a sort of underlying assumption, but I don't think there's any rigorous theorem in this direction.
Okay, and coming back to the principal question of non-uniqueness. So if I understand it correctly, then the plaidoyer is to just look for solutions that satisfy certain estimates, and then you're just happy with a set of solutions and regard them basically as well. They have the same legitimacy.
Yes, okay. So I mean, the question is really how to reconcile theory with experiment, and I think the theory, I mean, let's say the experiment is pretty clear that there's no uniqueness. I mean, of course, it's a question of sensitivity of initial data. So in some sense, there is uniqueness, but we have to idealize something. So we may as well just stick with the idea that uniqueness is not so important. If we perform the same experiment with a turbulent fluid, we will observe some universal features, but we will never see exactly the same flow twice. I think that's pretty intuitive. And so what my plaidoyer is that we should, I mean, one has to ask the right questions, and then and I mean, okay, so in terms of this convex integration and weak solutions, I guess the emphasis is not so much on the actual construction of the weak solutions. There are different ways of doing that now, but the important quantity is this average, this V bar, and the Reynolds stress tensor, and what sort of bounds does it satisfy. So in the examples I gave, in the first one, I don't know what is the good question. I was just emphasizing on the Navier-Stokes equations that compactness is the divide between existence by compactness and existence by convex integration. Whether that's the same divide as the uniqueness, of course, is an important open problem. In the second question, in the second example, I was trying to argue that when you look at these vortex sheets, different regularizations or small perturbations of the initial data lead to different behavior in its detail, but there is some coarse dynamics which is always the same. In particular, how fast do these roll-ups grow in time? How fast is the rate of energy dissipation, and so on. So, and these questions can be understood by looking at this relaxed system and trying to construct the average V and the Reynolds stress. And in the MHD, we still have to see how far we can go with this construction. That's very recent work, but at least there the message is that the relaxation, what is the relaxation, is very important in terms of what are natural bounds on the set of solutions. So like bounded solutions or even below. I mean, so magnetic helicity has to be conserved. That gives you a bound, and so on. I don't know if this was a good answer to your question.
Thank you very much. I'm just looking into the chat. Any
I have
further
a question. May I ask? So two questions actually. Question number one is regarding to the vortex sheet example. How were these numerical solutions produced? With what kind of a method? And also related to numerics and picking up this issue of non-uniqueness again, what does this imply for our predictive capabilities if we have these fundamental non-uniqueness issues?
Well, okay, so those videos were produced in MATLAB by Fran Mengual, but the numerics that he was using is, I mean, so we have, okay, maybe I can, yeah, here, can you see that?
Yes.
So the light blue curve, this is the vortex blob regularization. So you have the kernel of the Biot-Savart kernel appearing in the Birkhoff-Roth equation, and there's an extra like delta in the denominator to make it regular. And of course, you have to tweak a little bit so the numerics are stable enough to produce something for a sufficiently long time. Right, and of course it's with little sinusoidal perturbations of the initial data. The dark blue curve is the exact solution that we obtain from this formula. And in fact, so I was cheating a little bit. I told you that let's say this picture. So this Z, I mean, this mid curve is something that will also move in time. It has an evolution equation, but that's not exactly true. The only thing that it has in our construction is a Taylor expansion in time, up to, I think, third order. So beyond that, it's not really clear how to continue. I mean, there's no unique way. We don't have a, but I think that the main point here is to understand the how to continue the solution from a singular configuration. So what this type of non-uniqueness tells you about numerics? Well, I mean, the regularized vortex, the regularized Birkhoff-Roth equation, I mean this vortex blob regularization is okay, but the question is, if you let this regularization parameter delta go to 0, what happens? I mean, you have to pick something that gives you stable numerics, and then you get some picture, but how is that related to reality? And I mean, I don't know if there's any way to approach that problem numerically. Otherwise, it's, yes, I mean, in general, it's always a problem that any sort of numerical implementation has certain regularization somewhere. And if you are, I mean, if you're modeling an unstable situation, it becomes an issue. You can calculate your solution numerically, but how is it related to the singular case? Of course, in many numerical simulations, the regularization is not a problem because what you're kind of numerically computing is already a stable evolution. If you can prove stability of the full, I mean, the true equation, then regularizations are in general okay. I mean, that's of course very much a rough statement, but I think that's the main approach. Yeah. So here we don't have that. We don't have an equation that's stable in itself. So if you regularize that, you don't know what you get.
Okay. Thank you.
Further questions, remarks? This does not seem to be the case. So thanks once again, László. And well, goodbye, everybody. And of course, László, also from my side, the hope that we'll meet you in Chemnitz very soon. That'll be really nice.
That would be nice. Of course, in the command center.
Okay, yeah.
Give me a tour.
I can beam you up on the.
Oh yeah, okay, that's good.
Okay, Scotty. Okay, see you.
Thanks. Bye-bye.
Bye-bye.